In this video, we're going to look at a second bonding mechanism, and this time we're going to look at the bonding mechanism known as covalent bonding. Now, I've made a note alongside the title here that covalent bonding is the sharing of electrons, and we'll see what we mean by that in a moment. And this type of bonding typically occurs in two nonmetals. Now, a useful place to start here is to consider oxygen. Now, we know from earlier tutorials that the electron configuration of oxygen is 2,6 because oxygen has 8 electrons. And here we have 2 oxygen atoms drawn on the screen. Now we also know that each of these oxygen atoms wants to gain 2 electrons in order to become stable. It needs 8 in its outer shell in order to be stable. Now if we look at these oxygen atoms, neither of these is going to want to give up 2 electrons. They both want to gain 2 electrons. So we can't have an ionic bond form where we have the transfer of electrons from one atom to another. So instead what these two atoms do is they actually share electrons. And I'll just modify the outer shells here to show you what I mean. So if we look at the oxygen atom on the left hand side, we know that it had 6 electrons. So we've got 1, 2, 3, 4, 5, 6. And the same was true for the one on the right hand side. That had 6 electrons and still it has 1, 2, 3, 4, 5, 6. What it hasn't done is donate any electrons. Instead, the outer shells of both of those oxygen atoms have merged or overlapped, and now they're sharing the 4 electrons pictured in the centre. These electrons here. So if we consider why the oxygen atoms have done that, if we begin by considering the atom on the left-hand side, that atom on the left-hand side now believes that it's got 8 electrons in its outer shell because it has 6 of its own, plus the 2 that are being shared from the other oxygen atom. And vice versa, the oxygen atom on the right-hand side has 6 of its own electrons, plus the other 2 that are being shared by the other atom. Both of these oxygen atoms now consider themselves to be stable. And this is one of the main reasons why oxygen in our atmosphere always moves around in pairs. We see it written as O2, 2 oxygen atoms or an oxygen molecule when it's combined. We also see this behaviour in our halogens, chlorine, fluorine, bromine and so on. So rather than having an unstable outer shell, what they do is they share electrons in order to satisfy the requirement for a complete outer shell. So let's look at how this affects the bond between two nonmetals. So in the centre we have a carbon atom, and carbon has an atomic number of 6, therefore it has 6 electrons, and we see the arrangement here, 2, 4. Now carbon doesn't want to give up any of those 4 electrons, but at the same time it does want to have a complete outer shell. If we add in 2 oxygen atoms, then we see a similar behaviour. Our oxygen atom on the left hand side has an electron configuration of 2, 6, as does our oxygen atom on the right hand side. So for each of those we see 2 electrons on the inside shell and 6 on the outer shell. But what happens this time is our carbon atom, which requires 4 electrons to complete its outer shell, forms 2 covalent bonds with oxygen. So our oxygen on the left-hand side shares 2 electrons of its own with 2 electrons of carbon, and our oxygen atom on the right-hand side does the same. Now once again, each of these atoms have convinced themselves that they have a full outer shell because we have oxygen on the left-hand side, has 2 and 6 of its own, plus the 2 that are shared. We have carbon in the centre that has 2 on the inside shell of its own, plus 4, but then it's sharing 4 electrons from the oxygen. And the same for the oxygen on the right hand side. Now what we see pictured here is one of the products of combustion, the gas carbon dioxide, which is written as CO2, 1 carbon atom with 2 oxygen atoms. So pictured on the screen here we have a silicon atom in the bottom left corner and we have a carbon atom. Now we know that the electron configuration of carbon is 2, 4 because it has 6 electrons. And from the periodic table we know that the electron configuration of silicon is 2, 8, 4 because it has 14 electrons. So what we notice about each of these atoms is they both want to gain 4 electrons or share 4 electrons. So the way that I've pictured it here, we have silicon sharing 1 electron with carbon and carbon sharing 1 electron with silicon. But what this means is that the carbon still wants to gain 3 electrons, or it wants to create 3 more shared pairs of electrons here, here and here. And what we also notice is the same is true for silicon. Silicon either wants to gain or share another 3 electrons. Now what we have pictured here is the substance silicon carbide, and the chemical formula is SiC. Now silicon carbide is a ceramic material, and we know from earlier tutorials that ceramic materials tend to be very hard, very strong and very brittle. Now if we study silicon carbide in a bit more detail, what we find is that it forms a complex covalent network where each carbon atom will connect to 4 silicon atoms and each silicon atom will connect to 4 carbon atoms. And I'll just picture this on the right hand side. I'm going to fill in the carbons as shaded, and I'm going to fill in the silicons as open circles. So if we have a carbon here, that carbon is going to want to join to 4 silicons. But that's not the end of the story, because each of these silicons is going to want to covalently bond to 4 carbons. And this is going to repeat, because now we have a carbon that wants to form a bond with 4 silicons, and so on. So hopefully you can see that over time this is going to form a very complicated network, and that's known as a covalent network. Each of the electrons that we've highlighted there is going to join to another atom of the opposite material. Now because these covalent bonds are very strong and we get these large complicated networks, the material is very strong and it's also going to be rigid, hard and brittle. Now we'd see a very similar behaviour in things such as silicon oxide and various other different oxides, carbides and nitrides that make up this group of ceramic materials. So ceramic materials have complex networks of covalent bonds. Let's move on and look at one more final example, and this is also an important example because it forms the basis of the bonding in our polymers. Now we have various different polymers, and the most common polymers have carbon chains, and I'll give you an example. One such polymer would have chains that appeared something like this, where we have numerous carbon atoms surrounded by hydrogen atoms. We can get variants on this. It might be carbon atoms with, say, chlorine atoms. But what we see here is we see 2 non-metals bonded together. Now we already know that the likelihood is that's going to be covalent bonding, so let's examine this a little bit more closely. So we know that carbon has the electron configuration 2, 4, and we know that hydrogen just has the electron configuration 1. We know that the hydrogen, in order to have a complete outer shell, needs to gain or share 1 electron. And we know that carbon, in order to have a complete outer shell, needs to gain or share 4 electrons. And this is why we see each carbon bonded to 4 other atoms. Now for simplicity, we're only going to represent the outer shell of the carbons, but carbon has 4 electrons in its outer shell. And I'm going to represent these as X's or crosses. And there's one of those carbon electrons present in each of those shared bonds or covalent bonds. Now hydrogen only has 1 electron in its outer shell, but it's also going to share that with our carbons. Now what we see happening here is our hydrogen on the far left hand side now believes that it has 2 electrons, as does our hydrogen at the top, our hydrogen at the bottom, and our carbon in the centre believes that it has 8 electrons in its outer shell because it includes these 2 here where it's sharing with the next carbon along. Let's repeat that for our second carbon. Our second carbon has 4 electrons, 1, 2, 3, and we've already drawn one of them in the carbon to carbon bond. The hydrogen at the top contributes 1 electron, The next carbon in the chain contributes an electron. The hydrogen at the bottom contributes an electron, and so on. Now, once again, all of those atoms in that arrangement believe that they have a full outer shell. So what we end up with is a very stable polymer chain. What I've drawn here is the polymer known as polyethylene. Now, once again, because we have two non-metals in this chain, what we end up with is covalent bonding throughout the polymer chain. As I mentioned, there's various other different configurations of this, because what we could see is one of the hydrogens replaced with a chlorine. And I'm going to replace the hydrogen in the far bottom right-hand corner with a chlorine. This will give us a slightly different polymer with slightly different properties. But chlorine has the electron configuration of 287. Now, once again, we see that that chlorine isn't going to be prepared to give up its 7 electrons. Instead, it wants to gain one. But the carbon won't donate an electron, but what it can do is share an electron. So we see the carbon and the carbon sharing electrons, here and here, as we did previously. We see the carbon and the hydrogen at the top sharing electrons, and we see the carbon and the hydrogen on the right sharing electrons. And what also happens is the carbon shares an electron with the chlorine. Bear in mind, chlorine has 7 electrons in its outer shell. We'll draw these. But by sharing the electron with the carbon, it now believes that it has 8 electrons in its outer shell. And this is the basis of all of the bonding within chains of polymers. The important things to remember is that covalent bonding is electron sharing, and it occurs between two non-metals.